Astronomers just measured the mass of a planet with no star, a world drifting alone through interstellar space 9,800 light-years from Earth. This is the first time scientists have directly determined both the mass and distance of a rogue planet. Published January 1st, 2026 in Science. Right now, this planet is moving through the Milky Way with nothing to orbit. No sun, no light, no heat beyond the faint glow of cosmic background radiation. It weighs 0.219 Jupiter masses, roughly equivalent to Saturn, and it is traveling at speeds consistent with ejection from a planetary system. The breakthrough came from simultaneous observations by ground-based telescopes and the Gaia Space Telescope. When the planet passed in front of a distant star, its gravity bent the star's light in a microlensing event. Ground observers saw the brightening first. Gaia, positioned 1.5 million kilometers from Earth, saw it approximately 1.9 hours later. That time difference broke the mass-distance degeneracy that has prevented direct mass measurements of rogue planets for decades. Dr. Subo from Peking University, lead author of the study, stated, "You need to have this fundamental measurement of mass to really know it's a planet. Getting this kind of data opens up lots of doors to understanding more about a planet's possible origins and history. Still more significant, statistical comparison with other microlensing events and simulations indicates this object likely formed in a protoplanetary disk, like a planet, not in isolation like a brown dwarf. Dynamical processes then ejected it from its birthplace. This confirms rogue planets are not failed stars. They are planets that lost their homes. Here is what should concern you most. If billions or even trillions of rogue planets exist in the Milky Way alone, as current population estimates suggest, then planetary systems are far more unstable than models predict. Ejection is not rare. It is common, and the universe contains more homeless worlds drifting in darkness than planets orbiting stars. Think about that. Before we explain how astronomers measured a planet they cannot see, if you want to stay updated on discoveries that change our understanding of planetary systems and how they evolve, hit subscribe and turn on notifications, because what we are about to reveal will make you rethink what it means to be a planet. Leave a comment telling us, did you know there might be more rogue planets in the galaxy than planets with stars? Let's start with what a rogue planet actually is. Also called free-floating planets, these are worlds that do not orbit any star. They drift through interstellar space, traveling alone. They are not binary companions. They are not circumbinary planets orbiting two stars. They have no gravitational anchor to any stellar system. Rogue planets are completely dark. They do not emit visible light. They do not reflect light from a nearby star because there is no nearby star. Any residual heat from their formation has long since radiated into space. The only energy they receive is from cosmic background radiation and occasional gravitational interactions with passing objects. For all practical purposes, they are invisible. That makes them extraordinarily difficult to detect. You cannot image them directly. You cannot measure their spectra. You cannot track their orbits because they have no predictable orbital motion relative to a host star. The only way to find them is through their gravitational influence on background light. This technique is called gravitational microlensing. Einstein's general relativity predicts that mass curves space-time. When light from a distant star passes near a massive object, the light's path bends. If the alignment is precise, the foreground object acts as a gravitational lens, magnifying the light from the background star. The effect is temporary. As the foreground object moves relative to the background star, the alignment changes. The star brightens as the lens approaches perfect alignment, peaks when alignment is optimal, and fades as the lens moves away. The entire event typically lasts hours to weeks, depending on the mass of the lensing object and the geometry of the alignment. The shape of the light curve reveals information about the lensing object. A simple microlensing event caused by a single point mass lens produces a symmetric light curve described by a standard formula. The peak magnification depends on how closely the lens passes in front of the star. The duration of the event depends on the lens's mass, distance, and velocity perpendicular to the line of sight. The characteristic scale is called the Einstein radius. This is the angular separation at which the gravitational deflection is strongest. For a planetary mass object at typical galactic distances, the Einstein radius is on the order of milliarcseconds. That is thousands of times smaller than the resolution of most telescopes, which is why microlensing is the only practical detection method for these objects. Analyzing the light curve allows astronomers to extract parameters like the Einstein crossing time, which is how long it takes the lens to traverse one Einstein radius. For the rogue planet detected in this study, the Einstein crossing time was measured with high precision from the combined ground-based and Gaia data. That precision was critical for determining the mass and distance independently. Microlensing has been used to detect rogue planets since the early 2000s. Surveys like OGLE, operating from Chile, and KMT-NET, with telescopes in Chile, South Africa, and Australia, monitor millions of stars in the direction of the Milky Way's galactic center. When a star brightens unexpectedly in a pattern consistent with microlensing, astronomers analyze the light curve to infer properties of the lensing object. OGL, the optical gravitational lensing experiment, has been running since 1992. It is one of the longest-running microlensing surveys and has detected thousands of microlensing events, including several caused by planetary mass objects. KMT-NET, the Korea Microlensing Telescope Network, began operations in 2015 and consists of 3 identical telescopes distributed across the southern hemisphere. The network provides continuous coverage of the galactic bulge, where microlensing events are most frequent. Before this discovery, astronomers had detected approximately a dozen rogue planet candidates through microlensing, but none had directly measured masses. The masses were inferred statistically by analyzing the distribution of Einstein crossing times and comparing them to models. Those statistical estimates suggested that many rogue planets are less massive than Jupiter, with some potentially in the super-Earth or even Earth mass range. The challenge was always the same. Without knowing the distance, you cannot determine the mass from the light curve alone. Some candidates might be nearby low-mass planets. Others might be distant higher-mass planets. The degeneracy could not be broken with ground-based observations alone. But there is a fundamental problem. But the mysteries don't stop there. The problem is called mass-distance degeneracy. The same microlensing light curve can be produced by different combinations of mass and distance. A low-mass object close to Earth can produce the same brightening pattern as a high-mass object farther away. Without independent information about either the mass or the distance, you cannot determine both. For decades, astronomers have detected microlensing events consistent with planetary mass objects. Some are clearly planets orbiting stars, detected through binary microlensing signatures, but others show no evidence of a stellar companion. Those are rogue planet candidates. However, without breaking the mass-distance degeneracy, their masses remain uncertain. Population statistics help. By analyzing large numbers of microlensing events, astronomers can estimate the typical masses of rogue planets. Those estimates suggest many are less massive than Jupiter. Some may be Earth mass, some may be super-Earths. But those are statistical inferences, not direct measurements. The discovery reported in Science changes that. The rogue planet, designated KMT 2024 BLG 0792 by the KMT-NET survey and OGL 2024 BLG 0516 by the OGL survey, was detected during a short microlensing event in 2024. Multiple ground-based telescopes observed the event. KMT-NET telescopes in South Africa and Australia recorded the brightening. OGL in Chile captured it as well. What made this event unique is that the Gaia Space Telescope also observed it. Gaia, operated by the European Space Agency, ended its mission in January 2025 after mapping the positions and motions of over 1 billion stars. During its final year of operation, it monitored stars for microlensing events as part of its photometric science alerts program. Gaia is positioned at the second Lagrange point, L2, approximately 1.5 million kilometers from Earth in the direction opposite the Sun. That distance is sufficient to create a measurable parallax effect. Parallax is the apparent shift in an object's position when viewed from 2 different locations. Here's where it gets really strange. Humans perceive depth because each eye sees a scene from a slightly different angle. The brain combines those views to infer distance. The same principle applies to astronomical parallax. By observing the same microlensing event from Earth and from Gaia simultaneously, astronomers could measure the microlensing parallax. Dr. Dong explained, "The difference is that the spacing between the eyes of we humans is a few centimeters, whereas Gaia is about 1.5 million kilometers away from Earth. We are able to use the same principle to extract the distance information of this rogue planet candidate, finding the mass and distance separately. The geometry was favorable. The microlensing event was located nearly perpendicular to the direction of Gaia's orbital motion. That rare geometry caused Gaia to observe the event 6 times over a 16-hour period, beginning close to peak magnification. The peak occurred approximately 1.9 hours later from Gaia's perspective than from Earth's perspective. That 1.9-hour delay is the critical measurement. It reveals how much the apparent position of the background star shifted due to parallax. Combined with finite source effects, which account for the fact that the background star has a measurable angular size, the parallax measurement breaks the mass-distance degeneracy. Finite source effects occur when the Einstein radius of the lens is comparable to the angular size of the background star. In those cases, the star cannot be treated as a point source. Different parts of the star's disk are magnified by different amounts as the lens passes in front of it. This creates subtle deviations in the light curve that reveal additional information about the lens. For KMT 2024 BLG 0792, finite source effects were detected in the high-cadence observations from KMT-net telescopes. The effect is small, but measurable with modern photometry. When combined with the parallax measurement from Gaia, finite source effects provide an independent constraint on the lens's distance. The combination of microlensing parallax and finite source effects is powerful. Parallax breaks the mass-distance degeneracy by providing information about the lens's angular position relative to the source star. Finite source effects break it by providing information about the physical scale of the system. Together, they allow direct determination of both mass and distance. The result? The lensing object has a mass of 0.219 Jupiter masses, with an uncertainty range of 0.075 to 0.046 Jupiter masses. That places it firmly in the planetary mass range. For comparison, Jupiter is 318 Earth masses. Saturn is 95 Earth masses. This rogue planet is approximately 70 Earth masses, slightly less massive than Saturn. The distance is 9,800 light-years, in the direction of the galactic center. The planet is moving through the Milky Way with a velocity consistent with having been ejected from a planetary system, not with having formed in isolation as a sub-brown dwarf. But there's another problem that nobody expected. How do we know it formed in a planetary system and was ejected, rather than forming in isolation like a brown dwarf? Brown dwarfs are objects too massive to be planets, but too low in mass to sustain hydrogen fusion like stars. They form from the gravitational collapse of gas clouds, not from accretion in protoplanetary disks. The distinction matters. If rogue planets are ejected planets, that tells us planetary systems are dynamically unstable. Gravitational interactions between planets or between planets and their host star can result in ejection. If rogue planets are sub-brown dwarfs that formed in isolation, that tells us star formation processes can produce very low-mass objects that resemble planets but have different formation histories. Dr. Dong and his team compared the properties of KMT 2024 BLG 0792 with statistical properties of other microlensing events and with predictions from planet formation simulations. The mass, the frequency of detection, and the spatial distribution all point toward a planetary origin. The object likely formed in a protoplanetary disk around a young star, accreted gas and dust, and reached Saturn-like mass before dynamical processes ejected it. Ejection mechanisms include planet-planet scattering, where two or more planets in a system interact gravitationally, with one planet gaining energy and escaping while the others remain bound. Another mechanism is stellar encounters, where a passing star disrupts a planetary system, flinging planets into interstellar space. A third mechanism is the death of the host star, where mass loss during stellar evolution weakens the star's gravitational hold on its planets. The fact that this rogue planet has a Saturn-like mass is significant. Saturn is a gas giant that formed beyond the snow line in the solar system, where temperatures were low enough for water ice and other volatiles to condense. Gas giants like Saturn and Jupiter form by first accumulating solid cores of rock and ice, then accreting massive gaseous envelopes. That process requires a protoplanetary disk. If rogue planets have masses and compositions similar to gas giants in bound planetary systems, the simplest explanation is that they formed the same way and were later ejected. The alternative, that they formed in isolation and coincidentally have the same masses, requires additional assumptions. Dr. Gavin Coleman from Queen Mary University of London, who wrote an accompanying perspective article in Science, noted, simultaneous space and ground-based observations of microlensing events could be applied in the planning of future exploratory missions and could lead to a better understanding of how planets form across the galaxy. And the data showed something that simulations hinted at, but observations had not confirmed. The number of rogue planets in the Milky Way is uncertain, but estimates are staggering. Population studies based on microlensing surveys suggest there could be billions, possibly trillions of rogue planets in the galaxy. That would mean rogue planets outnumber stars. There are approximately 100 to 400 billion stars in the Milky Way. If there are trillions of rogue planets, they represent a significant fraction of the galaxy's planetary population. Some estimates go further. A 2021 study analyzing microlensing data suggested there could be as many as 20 rogue planets for every star in the galaxy. If accurate, that implies 2 to 8 trillion rogue planets in the Milky Way alone. Extrapolating to the observable universe, with an estimated 2 trillion galaxies, the total number of rogue planets could exceed 1022, or 10 sextillion. Those numbers are speculative. Current microlensing surveys are sensitive primarily to planets more massive than Earth. Lower mass rogue planets, including terrestrial planets and super-Earths, are harder to detect. The true population could be even larger. Could any rogue planets be habitable? At first glance, the answer seems to be no. Without a star, there is no sunlight to warm the surface or drive photosynthesis. Surface temperatures on rogue planets would be close to absolute zero, far too cold for liquid water to exist. But subsurface oceans are a different matter. Moons like Europa and Enceladus in our solar system have subsurface oceans kept liquid by tidal heating. Tidal forces from Jupiter flex Europa's interior, generating heat through friction. If a rogue planet retains moons after ejection, tidal heating from the planet could keep those moons' interiors warm enough for liquid water. Alternatively, a massive rogue planet could retain enough internal heat from its formation to keep its own deep subsurface warm for billions of years. Geothermal energy from radioactive decay could supplement that heat. In principle, a thick hydrogen atmosphere could trap heat and maintain a habitable subsurface ocean, even in the absence of sunlight. These scenarios are speculative. No evidence currently exists for habitable rogue planets or moons, but the fact that billions of rogue planets exist means the possibility cannot be ruled out. Some fraction of them, perhaps a very small fraction, might harbor life in subsurface environments entirely disconnected from stellar energy. There is also the question of detection bias. Microlensing surveys are most sensitive to planets with masses between Earth and Jupiter. Very low-mass planets like Mars or Mercury produce microlensing events too short and too weak to detect reliably. Very high-mass planets, approaching brown dwarf masses, are easier to detect but less common. The duration of a microlensing event scales with the square root of the lens's mass. A Saturn-mass planet at 9,800 light-years produces an event lasting several hours. An Earth-mass planet at the same distance would produce an event lasting less than an hour. Current surveys observe each star approximately once per hour, so Earth-mass events are easily missed unless the timing is perfect. The Nancy Grace Roman Space Telescope will change that. Roman's infrared detectors will be more sensitive than current ground-based surveys, and its continuous monitoring cadence will allow detection of shorter microlensing events. Roman is expected to detect not only hundreds of rogue planets, but also a significant number of bound planets in wide orbits around their host stars. That will provide crucial context. By comparing the populations of rogue planets and bound planets, astronomers can determine what fraction of planetary systems eject planets and under what conditions ejection occurs. The data will test planet formation models and reveal whether ejection rates depend on the mass of the host star, the metallicity of the protoplanetary disk, or the architecture of the planetary system. The implications are profound. If ejection is common, planetary systems are less stable than previously thought. Simulations of planetary system dynamics predict that multi-planet systems undergo gravitational interactions that can lead to ejections, but observational confirmation has been limited. The discovery of rogue planets at Saturn-like masses suggests that even gas giants, which form in the outer regions of planetary systems and have relatively stable orbits, can be ejected. What does that mean for Earth? The solar system has been dynamically stable for billions of years. The orbits of the terrestrial planets and gas giants have not changed significantly since the solar system's formation 4.6 billion years ago. But that stability is not guaranteed. Gravitational perturbations from passing stars or long-term orbital resonances between planets could destabilize the system over very long timescales. The risk to Earth is extremely low. The solar system's architecture, with gas giants in the outer system and terrestrial planets in the inner system, is relatively stable. Jupiter acts as a gravitational shield, deflecting comets and asteroids that might otherwise impact Earth. But the existence of billions of rogue planets indicates that not all planetary systems are so fortunate. Now let's put everything together. Astronomers detected a microlensing event caused by a rogue planet using ground-based telescopes from the KMT-net and OGIL surveys. The event was also observed by the Gaia Space Telescope. The 1.5 million kilometer separation between Earth and Gaia created a parallax effect, with Gaia observing the peak magnification approximately 1.9 hours later than ground observers. That time difference, combined with finite source effects, broke the mass-distance degeneracy. The mass is 0.219 Jupiter masses, approximately 70 Earth masses, similar to Saturn. The distance is 9,800 light-years. Statistical comparison with other microlensing events and simulations indicates the object formed in a protoplanetary disk and was later ejected, making it a true rogue planet, not a sub-brown dwarf. This is the first direct mass measurement of a rogue planet. Previous detections relied on statistical inferences. This measurement confirms that rogue planets exist at planetary masses and that ejection from planetary systems is a real phenomenon. We are not saying that all rogue planets form this way. Some may be sub-brown dwarfs, some may have formed through other mechanisms, but the evidence strongly supports a planetary origin for this object, and by extension, for many other rogue planet candidates detected through microlensing. Dr. Dong stated, "The door is open to study this new emerging population of planets. So far, we only have a glimpse into this emerging population of rogue worlds and what light they can shed on the formation of the bodies in the planetary systems of the universe." And here is what this really means. The technique demonstrated in this study can be applied to future microlensing surveys. The Nancy Grace Roman Space Telescope, scheduled to launch by May 2027, will conduct an infrared microlensing survey expected to detect hundreds of rogue planets. Roman will observe above Earth's atmosphere, providing clearer data and longer observation periods. China is also preparing the Chinese Space Station Survey Telescope, CSST, and developing the Earth 2.0 mission, both of which include microlensing as key science goals. Simultaneous observations from space-based and ground-based telescopes will enable parallax measurements for many more rogue planets, allowing direct mass determinations. With those measurements, astronomers will be able to determine the mass distribution of rogue planets, test planet formation models, and understand the dynamics of planetary systems. The data will reveal whether ejection is equally common for gas giants and terrestrial planets, whether certain types of planetary systems are more prone to instability, and whether rogue planets retain atmospheres or lose them to space over time. So what do we know for certain? Rogue planets exist. They drift through the galaxy without orbiting stars. This particular rogue planet has a mass of 0.2119 Jupiter masses, similar to Saturn, and is located 9,800 light-years from Earth. It likely formed in a protoplanetary disk and was ejected through dynamical processes. This is the first direct mass measurement of a rogue planet, made possible by simultaneous observations from Earth and the Gaia Space Telescope. What don't we know? How many rogue planets exist in the Milky Way? Whether most rogue planets are gas giants or terrestrial planets, whether they retain atmospheres after ejection, how long they survive before being captured by another star or disrupted by gravitational interactions, and whether some rogue planets host moons that could, in principle, harbor subsurface oceans warmed by tidal heating. And here's the urgency. The Nancy Grace Roman Space Telescope launches this year, in 2027. Its microlensing survey will observe hundreds of rogue planets. Simultaneous ground-based observations will enable parallax measurements, providing direct masses and distances for each detection. Within a decade, we will have a comprehensive census of the rogue planet population. Because if estimates are correct and there are billions or trillions of rogue planets in the Milky Way, then the majority of planets in the galaxy are homeless. They formed around stars but lost their homes. They drift in darkness, traveling through interstellar space for billions of years with no light, no heat, and no hope of returning to a planetary system. The truth is this: planets are not as stable as we thought. Ejection is not rare, it is common. And the universe is filled with worlds that once had stars, but now have nothing except the cold, empty void of space. And the only way to understand how common ejection is, and what it means for the stability of our own solar system, is to find as many rogue planets as possible and measure their masses, distances, and velocities to determine where they came from and how they were cast out. If this video changed how you think about planetary systems and their stability, hit like and subscribe to this channel. We are tracking the latest discoveries in exoplanets and rogue worlds as they emerge, and you will not want to miss what the Nancy Grace Roman Space Telescope reveals when it begins its microlensing survey later this year. Leave a comment with your take. Did you know that there might be more rogue planets in the Milky Way than planets orbiting stars? And share this video with anyone who thinks planets are always found around stars. After this, they will understand that the galaxy is filled with homeless worlds drifting in darkness.